So Hamilton asked the following question. So here is dodecahedron. It has pentagons, and then at each vertex we have characteristics 3, and it has 12 of those pentagons, as the name says. And here is the graph that you can make. And we said last time we can always project the polyhedra so that their edges do not intersect. And here is the way to make that graph for dodecahedron. So for every two vertices, if they are connected by an edge in the space, then they will be connected by an edge on the graph. So he asked the following question: is there a path going through this graph of dodecahedron, visiting every vertex just once? And that's why the whole type of graphs, visiting every vertex just once, got the name Hamilton graph. And for example, here is for dodecahedron, really there is a Hamilton path, and it's just written here. How do you do it? To emphasize, oh, this is, by the way, from the National Curve Bank. So they have all kinds of banks where they have National Bank of curves or sequences for recursive sequences and all that. People just want to accumulate the result. One nice detail is, I don't know if you notice the corner. Let me make it a little bigger. Who wrote the program? Dr. Peter Avery from Miracosta College. So that's, so I thought I wanted to show you this. So let's go back to our definitions. I don't think I need this anymore. So again, I'm not going to write it on the board. Definition is that Hamiltonian path is the path that visits every vertex exactly once, and then if it's closed circuit, then we call it Hamiltonian circuit. But story about Hamiltonian circuits is much more complicated than story about Euler graphs or Euler circuits, because we don't have a theorem telling us immediately if we can have Hamiltonian circuit or not, and also we don't have definite procedure how to accomplish it. So things are much more open, and then there are some of the yes.
So if we want to show that something doesn't have a Hamiltonian circuit or path, we have to exhaust every possibility,
or show the reason why it cannot be. For example, sometimes you see if there are some special features of the graph, like when there is a bridge or something like that, then you cannot come back through that bridge or something, So if you cannot finish one piece and you have a bridge, then you must find the reason for it. So you don't have to visit all the possible circuits and show that they cannot happen, but to find the reason why it doesn't exist. But there is one positive result. So, for example, of course, this is a very simple graph, but generally for this one, even without trying it, we know that it does have a Hamiltonian circuit. Why? Because, again, look at the degrees. What is the degree here? What about here? 3, 1, 2, 3, 4, 1, 2, 3, 4. So generally, it's a heavily populated graph. That means there are lots of edges. So that's good for Hamiltonian paths. Why? Because you don't have to traverse them all, but gives you more options. Does that make sense? And there is a theorem that says, just better consequence, by Dirac. By Dirac, if have you heard about the name of Dirac in some other course? What's it?
Dirac delta function.
One more in physics as well, but that's not the same Dirac. No, the other one is French Dirac. No, this one, it's interesting story. This Dirac is a Hungarian guy, but he was adopted by the other Dirac. So he has his name. I never heard of any stories like that in mathematics. So we saw some families, but here Dirac was really, this Dirac from graph theory was adopted by the other Dirac from delta function. Anyway, so what is this Dirac consequence of Orr's theorem telling us? If each degree is at least half and half, then you have Hamiltonian circuit for sure. It doesn't tell you how to construct it, but it guarantees it. So if you look at this, how many vertices do we have here? 5 vertices. And what is the minimal degree of any vertex? Oh, this one has degree 2. Although, no, but then I have to go to original 1. So it doesn't satisfy Dirac's version, but Orr's theorem says, doesn't matter, you don't have to have half on your own, but together with any other graph, you must have 5. So for example, if you look at this one, this is the only one that has less than half. But what is degree of A? What about degree B? Together it's more than 5. And then what? If you take this E and this C together, what's the sum of the degrees? 5. And that's it. That's Orr's theorem. So Dirac is a special case. So you see Orr's theorem says if G is a simple graph, so there are no multiple edges between the vertices. So if G is a simple graph with n vertices such that any 2 vertices together have at least n joint degree, then G has a Hamiltonian circuit. And so theorem, that's a positive result, but you might have it in some other cases as well. So this is theorem of Orr, says a simple graph, G simple graph. And condition is, so it gives us sufficient condition. The degree of U plus degree of V is greater than or equal n. All right. Why is this? It's an interesting proof. How do you prove that here? Prove. Suppose that the G satisfies the condition, but it does not have a circuit. But it does not have a Hamiltonian circuit. So what are we trying to do? Yes, argue by contradiction. And we say the following. All right, let's keep enriching it, adding more edges, until it becomes heavily saturated. So let's G, and assume that that's without laws of generality. Assume that G is a maximal such subgraph, maximal such graph with n vertices. What do I mean maximal? You have n vertices, and you say, there's no Hamiltonian circle. Let me add one edge. And then what? And then if it gets Hamiltonian circuit, that's it. But so, can you add edge without making Hamiltonian circle? And as long as you can do it, you keep adding edges. Keep adding edges and suddenly say, no, whatever I add just makes Hamiltonian circuit. Can we always assume that? So we can think of it as fully saturated. Saturated before it gets a Hamiltonian circuit. But then what? Then what happens with such a graph? So when we add any edge, what will happen with that graph? So once again, G is assumed that G doesn't have a Hamiltonian circuit. But as soon as you add one more edge anywhere, it will get a Hamiltonian circuit. So what happens? We say, all right, let's add one edge. Edge to such G. What will happen? G has Hamiltonian circuits. Like this. But then what do? Let's remove it back. So remove it. So what is that telling you? So we add it. When we add such, it looks strange. Why are we adding it and removing it? For the following conclusion, and that's what's important. If I add it, it has Hamiltonian edge. When I remove it, it doesn't have any more, but what does it have for sure? Exactly, when you remove one edge, it's still connected, and so generally that reason was only used to show that there is Hamiltonian path between two vertices U and V. So, but there is Hamiltonian path in that one. So now what happens? Now here is the story. Let's say the degree of U is K. Why don't I do it with numbers? Okay, maybe we can go general. So the degree of U is K, degree of V is L, and I know that K plus L is greater than or equal N. So what is this telling you? It's telling you the following. U is connected with someone, and U is connected with someone else, let's say. So those are the guys that U is connected with. And we call that, I don't know, I think we call that T or S. Adjacent to V. T is connected, S are predecessors. So here are those that are connected. Let's call that S. Set S of vertices connected to U. How many of them are there? How many vertices are connected to U? I mean, don't count there according to the letters. What is degree of U? K. No, degree of U is K, so there are K vertices connected. So S has K vertices. And now what? Now comes some interesting combinatorial trick. So those are from S. S1 and S2, I can call them. But now we will consider in that path their predecessors. So I put the stars there. So before that dot is this star, and before this dot is this star. And that's called set T. T is the set of their predecessors. And we need just one more move in this abstract story and we will be done. And here's what I need. Can you argue why is V connected with one of those stars? And that's it. We'll now build Hamiltonian path and reach contradiction. Why is V connected with one of those stars? What is degree of V? L. And K plus L is greater than or than N. So, what is this telling you? If the degree of L is, if degree of this V is L, how many vertices can you fail to connect to? At most, how many? So, V, story of V. Connected with L. Not connected with how many then? If there are N altogether and you are connected with L, with how many are you not connected? N minus L. But from this connection, N minus L, L is less than or equal K. So what is that telling you? That this V can fail only to connect with K points. But how many stars do I have? K, because that's the degree of U. So there are K dots, and that's why there are K stars. So generally what? V can fail to connect only with K vertices. But look at this. V is for sure not to connect it with whom? With itself. So V fails itself, you know. And then what? No, I cannot do U because U might be one of the stars when I shift back, you know. So what? V is not connected to itself. So already not connected to less than K. Not connected with itself. And he's not a star because he's the last one. So he cannot be, that's why we go one ahead, to avoid V being one of the candidates. So what's that telling us? Not connected with itself. So he already takes one of those K places, he takes himself. So there are only K minus 1 stars that he can fail, but there are K stars. What is that telling you? One of the stars he doesn't fail. Must be connected with 1 star. So what is the story? So there is that path that goes like this around. Here is U, here is V. You have a dot, then you went back on the path to get the star, and then V is connected. Here is the story. And then what? U is connected with the dot. Can we make a circuit now from this picture? What do? You go from U. And then what do you do? Go along the path until you reach the star. When you reach star, what do you do then? Cross to V. Then you go backwards your chain, and then when you come here, you don't traverse that. When you come here to that dot point, you go back. Here it is. You go here. You go to star, which is one step before the dot that U is connected to. That one's connected to V. Then you finish the cycle and come back. Here's your circuit. So, which is contradiction. So we can make circuit, and that circuit go U with less labeling than in the proof in my notes, to star, then to V, to dot backwards, counterclockwise. To dot, and from dot back to U. Here it is. So that's one positive result that tells you that graphs that have high degrees have Hamiltonian paths for sure. So example, what if you have K5 graph? Although for this one it's quite obvious, even what it should be if you have K5 graph. What is the degree of every vertex here? 4. So it's heavily, because consequence of this theorem, as I mentioned, is Dirac's theorem, that if every vertex has degree at least half of n, then for sure you have Hamiltonian path. So this one obviously has it because degree of every vertex is 4, which is greater than or equal 5 halves. So that's one sufficient condition for having Hamiltonian circuit. And then you might ask why would it be so important to know to kind of build those Hamiltonian circuits. Probably the ideas come up easily, but here are a few examples. So examples, why is it important to know this? So here is an example of a nice usage of this. Suppose that we have a disk that has sectors. One, two, three, four, five, 6. Is this 8? 1, 2, 3, 4, 1, 2, 3, 4. Suppose you have 8 sectors on a disk. Yeah.
What does that say? U to star to V to something?
V counterclockwise. V goes counterclockwise because from U to star you go clockwise.
That's a C. It looks like a B.
Oh, I started something else, so I wrote on top of it something.
Okay, thank you.
Yeah, welcome. So it's very interesting applied problem. So here's the problem. Suppose you have sectors on a disk, and this is simplified. Just you have 8 sectors. And suppose you want to label them in a binary code. But you want to label them so that the neighbors never differ by more than 1 digit. So if this one is 0, 1, 0, then this one cannot be, no, this one's good. But if this one's 0, 0, 0, then next one cannot be 0, 1, 1. Do you understand the problem? So these two differ by 2 digits. Do you see that? Why is that important? Because there's always error in reading. So if you read 1 digit wrongly, you would like to stay, actually, at least if you read 1 digit wrongly, you will be at one of your neighbors, do you agree? Instead of going across. Because if you label so that, for example, 0, 0 with 0, 0, 0, 1, if you have them like this, this will be a bad idea because if I read this digit wrongly, I will go from one sector to the disk to completely opposite sector of the disk. So you can make a program that says, all right, read that sector and 2 neighboring sectors, and then you are sure that your information is in one of those. So if your addresses are written like that, that reduces the chance of the error. So here's the question. Can we label all these sectors so that neighboring sectors differ by at most by exactly 1 digit? Yes or no? So what's this? You can say what does this need to do with the Hamilton's graphs? We can say the following. If I call this A, B, C, D, E, F, G, H, okay? And then what? Then if they are neighboring sectors, then I will connect them with the edge, and then I want, if they are neighboring, I will connect them with the edge. So here it is, I'll make a graph. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0.
Don't those second and third
What?
differ by 2 digits though?
What say? Yes. So let's say 1, 2, 3, 4, 5, 6, 7, 8. Here it is. Okay. What? So no, I'm not saying that this is a good construction. This is just these are 8 vertices, and somehow I have to connect which ones will be neighbors. You know. So what? Then I have always so I would need to go like from 0, 0, 0 to 0, 0, 1 and say we are neighbors. And then who is your next neighbor? 0, 0, 1. Then I need to decide either 0, 1, 0. And generally what I'm doing is exactly I'm visiting all these 4 in a Hamiltonian path. So what? From 0, 0, 0 to 0, 0, 1 that's okay. They are valid connection. And who else is 0, 0, 0 good? 0, 0 with only 1. 0, 1, 0 is good. And 1, 0, 0, yes. And then 1, 0, 0 is okay with which one? 1, 0, 1, and so on. So generally, if they are valid neighbors, then you will connect them in the graph. And then if they are not valid neighbors, you will not connect them. So for example, those two 0, 0, 0 and 1, 1, 1 will not be connected because they are not valid neighbors.
Are all the 1, 0, 1, 0, 1, 1, 1, 1, 0, are those all connected because they...
No, this is not connected. Let me finish it. So here, this is validity connection. So I'm not, this is not Hamiltonian path. So these are valid connections. Is this valid connection? And 0, 0 is validly connected with this. Then what? 0, 1, 0 is already connected down. What about, who else?
The one to the right.
Exactly. So this is valid. What else? 1, 1, 1, 1, 0, just front difference.
One directly above 1, 0, 1.
1, 0, 1, 0. No, they have two differences. No, difference is on 2 spots. Just on one digit is read wrongly. So then what? 1, 1, 1 is connected with what? So for example, this one is connected because they differ only in the first digit. These are connected. And then what else? 1, 0, 0. 1, 0. All these two, yes. All right. So here is the graph. There might be some other connections. So the question is, how do I make those vertices on the, so what? If, when I make Hamiltonian path, then that's neighboring path. So I'll go from one vertex to another, say, here is the vertex I start with, here is my neighbor, this will be my neighbor, this will be my neighbor, and always neighbors are validly connected because they differ by 1 digit, and that's exactly. So if I make Hamiltonian path, that will exactly do what I need. So is there a Hamiltonian path for this one? And there is a beautiful way, what is it? Actually, this is all much easier if you put them on a cube. Then everything is very easy. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Agree? And actually, all these connections now we can read from there. So for example, here it is. 1, 0, 0 is connected with what? With 0, 1, 0, 0 is, no, this is not good. 0, 0, 1, 0, 0. 0, 0, 1, that's above. 1, 1, 0, and 0, 1, 1, 1. Yeah, okay. Doesn't matter. So here it is. What is the Hamiltonian path where we can visit all the neighboring, all the vertices that differ? So these two differ by 1 digit. These differ by 1 digit. These differ by 1 digit. These differ by 1 digit. This is, and so on. So can we connect all those vertices so that they only differ by 1 digit? Can we find a Hamiltonian path on this graph using this cube? So what would that be? You start with 0, 0, 0, and you go to 0, 0, 1. Is that valid connection? Then what is the next one? 0, 0, 0, 1, 0, generally,
Straight up.
So diagonal.
1, 0, 1. No. 1, 0, 1, yeah.
The 0, 1, 1 and the 0, 1, 0 are reversed.
Oh, yes. I wrote coordinates wrongly, sorry. Yes, so this is 0, 0, 0, 1, 1, 1, and 1, 0. And this is 1, 1, 0, and this is 1, 1, 1. Yeah, thank you. So what is it? Then we go here by 1 digit. We go here, done again difference in 1 digit. What happens here when I go?
Just one digit.
The last one. And then, of course, we're not going to close it here because we would finish the path, but what are we going to do now? You go up, and when you go up, how many digits are changed? Only one. So whenever you traverse a lower dimension, you change just 1 digit. So here it is, you go up. Now you traverse the same shape, but now in the opposite direction. Why? Because I want to end here, do you agree? So I'm not going to go this way. I will go this way, I will go this way, I will go this way, and finally I'll come back. So traverse the bottom. So when you start like this, traverse the bottom this way, go up, traverse the top the other way direction, and connect back. So then we can just place all of them in the sectors. So here is how it will be. So they are all neighbors, 0, 0, 0. 0, 0, 1, 0, 1, 1, 0, 1, 0. And then we'll get 1, 1, 0. And then we'll get 1, 1, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0. And that's next one. What if it's 4 digits?
You know, Q in China make
Here's the one. So what happens here, you can just find it in the notes, you actually need 4-dimensional cube. How do you draw a 4-dimensional cube? The same way. 3-dimensional cube takes 2 squares and connect them, do you agree? With parallel edges. What about 4-dimensional cube? I don't know if you can see clearly. You see that there is a little cube and the large cube. Do you see little cube and large cube? So generally, this is what you do. You actually finish 1 cube like we did here. Go into lower dimension, finish the lower dimension, and then connect and finish the upper dimension. So the same way here, you can finish the whole, this cube, until you are almost ready to, you don't close it completely. Then you go to the outside cube, finish the outside cube, and come back. So just, I'll look at it. In my notes, generally there is a red line for the Hamiltonian circuit. All right. What else? Let me just show you one interesting example. I didn't put it in the homework, but I'm curious how you will solve it. Here's the question. Another example. Just quickly, 2 minutes to just formulate it. Suppose that we have 5 teams that do the apartment fixing. And here are the teams. Team A, for apartment A, you need 7 hours. What do you do first? Carpet or no, you paint and then you carpet the apartment. So painting team and carpeting team. So apartment A, 7 hours to paint, 3 hours to carpet. B, let's say, 9 hours to paint and 5 hours to carpet. C, let's say 10 and 1. D is 6 and 2, 6 and 4. Okay? So you want to organize job between these teams. So here are the rules. So you have one team that does painting and one that does carpeting, and you want to minimize the waiting time. So you want just to finish the job as soon as possible. How should you order the job to be done? So they don't work simultaneously. So where would you send painters first? Of course, first you need to send painters somewhere, do you agree? And then carpenters are waiting everywhere. So where are you going to send painters first? Are you going to send them in A, B, C, or D? What's
the
A?
lowest one, right? So E, the seven. Oh, what's the six? Oh, it's a six. That looked like an eight.
Oh, 6 here.
So then we leave to the smallest one where they need the smallest amount of paint.
Not necessarily, because later on it might cost you. Then this guy might employ the carpenters too long, you know. So it's not like one job in the beginning. You might gain in the beginning and then lose later on because it goes in the wrong direction. So here it is. Generally, for each of them, you need to see what's better between A and B. Who are you going to choose? If there are just 2 apartments, which one are you going to choose? Think about it. And then between A, B, C, and D, make arrows in directed graph for advantage. So advantage, if A has advantage over B, put an arrow this way. If B should be ahead of A, put it this way. Then your whole project it needs Hamiltonian path, although in a directed graph. So think about this. If I have this, between A and B, who should be done first? Let me cross it here, 6. Sorry. Now it's more interesting, yeah. So how do you decide who what's say?
A, because the carpet still takes less than painting on B.
That's not the argument. So just, here it is. Do the calculation. How long will it take if A starts first? How long will it take everything to finish if A starts first? So what? A painter takes how much?
7 hours.
7 hours. Painters take 7 hours. Then what's happening in apartment B? They are waiting all the time. Do you agree?
Right.
And now what? Now
Painters go through apartment B and start painting while the carpenters are starting to lay carpet in apartment A.
okay, so calculate that, and then if B starts first, and then see what is the total time, and that will give you the rule. Actually, starts with the other few games, and then you will have the arrow, then make Hamiltonian graph, and you will get the procedure. We'll talk about it.
We have to do this for all of them. Then
For each pair, for each pair who has advantage, and then you want to go down the Hamiltonian.
Then we compare B to C, and then we compare C to D. And then
But generally, when you make a rule, then it's easy to. If you make there is a kind of rule of thumb that helps you to solve all of them. So do it in an abstract way.
You also want to minimize the amount of time.
You just want to minimize time that's taken from the beginning till the end. That's the goal. Minimize the total time that everything is done.